we'll talk about this title. So please start.
Yeah, thank you for introduction. Yeah, today I will talk about this title. So in this talk, we propose three methods to calculate the hadron mass spectrum in the framework of the Hamiltonian formalism in the this model to flavor string model. And this work is based on the collaboration with Ito-san and Tanizaki-san in YITP. So I start. Okay, so I start from why we considered Hamiltonian formalism. So recently, tensor network method and quantum computer is rapidly developing. So this fact motivated us to simulate quantum field theory in the Hamiltonian formalism. So the reason is that there is some advantages like this. So one, maybe the well-known advantage is that this method is free from the time problem, which usually frequently happen in Monte Carlo method. So at this point allow us to study, for example, chemical as a model with chemical potential or Volcker theta term. And the other advantage is the Hamiltonian formalism is good at real-time evolution. So it's an operator formalism. So we can construct a time evolution operator explicitly, and so by acting such operator, so that we can evolve the state. So in this method, maybe we can study some scattering process. And other advantages, so the Hamiltonian formalism, we can easily treat excited state. So this point is related to this work, and in fact, we can investigate the mass spectrum of the model using this property. So in fact, the Hamiltonian formalism can be a novel non-perturbative approach to simulation quantum field theory. So we want to consider this possibility. And in fact, for example, the QCD, quantum chromodynamics is an important example where the non-perturbative effect is essential. So if we can establish this kind of nice non-perturbative method, we can apply such a method to QCD. So as I said, so QCD non-perturbative effect is important. So for example, let me show where such an effect is important. So one of the important issues of QCD is mass spectrum, or hadron. So hadrons we can see in the experiment, but so it is not that such a hadron composed from clocks, for example, up or down, and it is not that up clock and down clock is the mass is roughly a few MeV. On the other hand, the composite particle, like up, down, that is proton. Its mass is more than 900 MeV. So it's much larger than just a combination of these masses. So it's like this picture. So it is unknown that why this kind of behavior is observed. And to investigate this problem, the non-perturbative approach is very essential. And successful application, this is actually the successful application of the lattice Monte Carlo simulation. It is a well-established non-perturbative method, and which is a Lagrangian form. And in the Monte Carlo simulation, the hadron masses are obtained from the correlation function. So this is an example. So we can, for example, measure the correlation function of the pion, which is denoted by this red line. So this is a plot of the correlation function against this imaginary time tau. And so the red line shows the pion result, and the blue dot shows the low meson result. And correlation function typically behaves like an exponential to the minus m tau. M is the mass of the corresponding hadron. So from this result, from this slope, we can extract the mass of pi and rho. And in fact, the slope of low meson is more steep. So it suggests that the low meson is heavier than pi meson. And from this kind of result, we can reproduce the mass spectrum of the various kinds of hadron. This is a comparison of lattice result, red point, and experimental result is shown by horizontal bar. And in this calculation, there is three mainly three input. Yeah, because in this setup of QCD there are three parameters, but only three inputs we can reproduce more than 10 species of hadron. So it's very nice. But, yeah.
Excuse me.
Yes.
So at the large time, the correlation function gets larger. So is that because of backward propagation?
So you mean the y go up again?
Yeah.
So in fact, this behavior is a cosine hyperbolic. So in this simulation, we apply a periodic boundary condition. So in periodic boundary condition, the correlation function go down and again go up. Yeah.
So that is because of backward propagation. Wrap around.
Backward.
Yeah, probably you are saying the same.
Yeah. Because on the circle.
Yeah. Okay.
Yeah. This point.
Yeah, it should have some periodicity.
Yeah.
Okay. Thank
you. Okay. So yeah, this is some interesting example of non-perturbative effect of QCD. So we want to study this kind of things in Hamiltonian formalism. So let me show current status of the Hamiltonian simulation of quantum field theory. So one of the popular model is the one flavor mass distribution model with maybe possibly including theta term. So this is because this model is the simplest non-trivial gauge theory which shares some features with QCD. So this model is very nice, good, just one. Yeah. And in fact, there are some recent works which compute some potential or mass spectrum for this model. Yeah. But this model is just one flavor. So in fact, it is interesting to extend the number of flavor to 2, because in this case, we can introduce isospin symmetry. So then we can see something like meson by analogy with QCD. So it's very interesting. Yeah. So our aim of this work is we want to develop method to compute the hadron mass spectrum in the Hamiltonian formalism. They are focusing on two-flavor Schwinger model. So let me explain briefly the two-flavor Schwinger model. So this model is a 1+1D quantum electrodynamics. Is two species of Dirac fermion, and Lagrangian is given by this. There are some parameters. So G is coupling constant, and M is mass of fermion. Yeah, and theta here is a theta angle. And this model has some symmetry. For example, charge conjugation and the parity. So this discrete symmetry exists in when the theta is pi times some integer. And also, as I said, so there is a SU2 symmetry acting on the flavor doublet. Yeah, there is some. F denotes the flavor as the index of flavor. So this we call this symmetry isospin symmetry. So due to this symmetry, the composite particle appears as singlets or multiplet of this isospin symmetry. So we call this composite particle meson. So there are some. This is some list of the possible composite particles. This is pion, and this is eta meson, and this is sigma meson. Yes, this 1 and 2 represent the flavor. So due to this property, this two-flavor Schwinger model can be a good toy model of QCD with up and down goals.
Excuse me, sorry,
Yes.
I don't know much about this model, but is this asymptotically free theory?
Yeah.
Oh, okay, thank you.
So
So it,
yeah.
so it is that does that depend on the number of flavor?
For example, one flavor is also a simple tree, and I'm not sure much about the many flavor case.
But for this case, gauge coupling had a positive mass dimension. So
Ah,
Yeah. Yeah.
I
Maybe.
think
okay.
it's always a
Yeah, yeah.
symmetrical flavor.
Uh-huh.
Yes.
I see.
Yeah. And this model, so if massive case, I mean, if m is non-zero, so this model cannot be solved exactly. But the bosonization technique is available. Yeah. So this technique means so the fermionic system can be mapped to the bosonic system, and so we consider strong coupling region. So G is much larger than M, but M is non-zero. And the corresponding bosonized Hamiltonian is given by this. And there's a two pseudo scalars, phi plus and phi minus. Yeah. And in fact, this one of the scalar phi plus corresponds to eta meson. And you can see that this term is mass term of phi plus. So you can estimate that the mass of eta meson is order mu plus some correction with mass with order m. Yeah. And mu is given by this relation. And there's a, in fact, it is not, there's a soliton and anti-soliton of phi minus. And also the bound state of these soliton and anti-soliton. So this kind of things is described by so-called Sine-Gordon model. In fact, if we can ignore the propagation of phi plus in this model, so this model reduced to Sine-Gordon model. Yeah, and this model describes this kind of soliton state. And this soliton and anti-soliton describes the pi meson. Yeah. And mass is roughly given by this. And also, the bound state gives a sigma meson. And interestingly, so because of the property of Sine-Gordon model, the mass of pi meson and the sigma meson is related by this formula. It's a square root 3. So this number comes from the specific interaction which comes from this coefficient to square root 2 pi. And by summarizing these results, so in the small mass region, we may find this relation. The lightest meson is pion, and the next is sigma with this ratio, and heaviest one is eta. Yeah, and the fact that eta is heavier than pi is known as a U1 problem in QCD. It's related.
Excuse me, how can I see flavor symmetry
In,
at this level? Yes.
Actually, in fact, this model has isospin symmetry, but it's very non-trivial, and maybe we cannot directly see, in this form. Yeah, it's very non-trivially, hidden.
I see. Anyway, at the level of Lagrangian.
Yeah, it has.
Okay.
And actually, also Sine-Gordon model, this approximation comes from the ignoring eta meson. It's an isosinglet state. So in that sense, Sine-Gordon model still has isospin symmetry. So which is mainly discussed in this case. Okay. So it is nice to confirm this kind of prediction by numerical simulation. And in fact, there is a previous work using Lagrangian formalism, the lattice Monte Carlo simulation. And so we can, of course, we can calculate the pion mass and eta mass, but there's some possible difficulty. So difficulty in Lagrangian formalism is that, for example, about sigma meson. So this meson has the same quantum number as vacuum because maybe I'm sure. So it actually it is scalar with parity even. So in that sense, So it's the same quantum number as vacuum, so it's difficult to extract clear result due to the statistical noise or some effect. And also about eta meson, it is the heaviest one. So it is also not difficult. And this is actually the example in this paper. So this circle represents the correlation function of pi meson, which can be measured nicely. But for eta meson, this black square, so only 4 points here, and statistical error is much larger. And also, if we turn on theta term, the severe sign problem appears. And in particular, the theta around pi is difficult. So this is a pi on mass against the theta over pi. And this is theta 0, so it's okay. But if we approach theta pi here, so the signal is very noisy. So let me explain what we did in this work. So in this work, we proposed 3 methods to compute the hadron mass spectrum for tensor network of quantum computation. And one is that we call the correlation function scheme. As name suggested, this scheme, this method is a generalization from the Monte Carlo method. I mean, usual technique of correlation function in Monte Carlo. So, but compared with the Monte Carlo case, so if we use tensor network, so tensor network doesn't have statistical error. So in fact, not only pi on, but also sigma and eta meson can be measured precisely without statistical error. This is one of the nice points. And the second method we called one-point function scheme. So in this scheme, we use the boundary effect. So in fact, we impose open boundary condition in the simulation. So if we are interested in the physics in infinite system, the boundary effect should be eliminated usually. But in this scheme, we use the boundary effect. So then we can obtain the mass spectrum again. And the feature of this scheme is most economical. I mean, the computational cost is most cheap, and also suitable to MPS, I mean, tensor network. And third one is dispersion relation scheme. So we directly generate the excited states. This maximally use the feature of Hamiltonian formalism. And then the quantum numbers and momentum can be obtained straightforwardly by measuring such a state. So from such information, we can obtain the mass spectrum. So we demonstrate this method in the two-Kleber-Schwinger model by using a tensor network, TMRG. So it's the end of introduction. So please, the question is welcome anytime. So we go next. We briefly explain Hamiltonian formalism of two-Kleber-Schwinger model. So in the previous page, I explained the continuous theory. So we now introduce a lattice theory. I mean, lattice Hamiltonian. And this is Hamiltonian. And there's some parameter. A here is the lattice spacing. And N here in the sum is a number of lattice sites. I mean, system sites. And this MRAT is mass parameter, but we add some correction term considering order A correction. This can be discussed. This is discussed in this paper. And this U is a so-called link variable, which represents a gauge field. And L here is a conjugate momentum of gauge field given by this. And about fermion, represented by this chi. So we employ the so-called staggered fermion formalism. In this formalism, originally the Dirac fermion is 2 component in 1+1 dimension, like this. But in this fermion, staggered fermion, these 2 components are decomposed And one of the component is assigned on the even side, and the other component are assigned on odd side. So the chi itself is just a single component. So, and yeah, let me define the charge density. It's a psi bar gamma 0 psi in the original Dirac fermion. And then the Gauss law condition is given by this formula. It's a relation between the divergence of conjugate momentum L and its charge density. So in that sense, L is it can play a role of electric field. And the point of this 1+1 dimensional Schwinger model in this open boundary condition is that we can solve the Gauss law constraint explicitly, because we can just adding this equation from left to right, yeah, over all the sides. I mean, integrate this equation by setting some boundary condition. Yeah. Then so Ln is just given by this form. It's purely fermionic operator. So it's composed of fermionic operator. So then it's nice. Yeah. So originally the gauge field has infinitely large Hilbert space, but thanks to this property, the Hilbert space can be finite. And also, link variable can be set to identity by using the gauge degree of freedom of Q1 phase. So then, the resulting Hamiltonian is just this. So there is only Stuttgart fermion. Yeah, there is no gauge field. So it's nice. Yeah, it's very convenient to handle. And once we obtain this kind of Hamiltonian, we can use the so-called Jordan-Wigner transformation. So this transformation is map the fermion operator to the spin operator. I mean, Pauli matrices, like this kind of relation. And if you are familiar with usual Jordan-Wigner transformation, for one flavor case, it looks very strange. It's a mix. The flavor is mixed. Yeah, in this program. But the reason why, actually, there's some option. It's not unique, but the reason why we employ this combination is that we can map the local operator in nicely. I mean, in compact way. So if we employ the other choice, maybe that some operator can be very non-local. So in that sense, this choice is very convenient. Yeah. And so that's after Jordan-Wigner transformation, we obtain the spin Hamiltonian, and it is good to apply the tensor network or quantum computation. Yeah, it's given by it. So as I said, only a few combination of Pauli matrices appear, so it's very nice. So okay, I introduced Hamiltonian. So then I will show how to analyze that Hamiltonian. So we employ the tensor network method, and to express the state, I mean the eigenstate of Hamiltonian, we use the so-called matrix product state, MPS. So this state is written like this form. So A here in the trace is some complex matrix if we fix this spin index. And so maybe it's good to see in the diagram. So this green box represents this matrix A. So this leg S0, S1 represents a spin up or down. So only 2 dimensions. And this horizontal legs represents a size of a matrix, di minus times di. So in general, it can depend on the side. And yeah, so this d assigned of each is horizontal legs is called the bond dimension. So, and the property of this MPS is that if this matrix size D can be arbitrarily large, so MPS can represent any state in Hilbert space. But in practice, we
excuse me.
yes,
Is it true? I suppose matrix products I know that matrix product state can be represent the short range entangled state, but I don't know how this MPS how much ability to represent more long range entangled state.
yes, yeah. In fact, if we restrict the D to the finite value, in that case, I mean, the state is reduced to just approximation.
Yeah.
So in that sense, the gapped state can be nicely approximated by this finite D, but the gapless states is very difficult to approximate by finite D. In that case, the D becomes very large, actually exponentially large. And this arbitrarily large means mostly exponentially large. So if there's an exponentially large degree of freedom, it can represent the original exponentially large state, right? And in fact, if we have the complete wave function of the any state, some state, we can, in principle, we can obtain MPS by applying a singular decomposition, right, for any state. But maybe the bond dimension can be very large. But anyway, it can, in principle, possible. Yeah. The point is, how this approximation is good. Yeah, that is.
And here you are interested in gapped case.
Yeah,
Yes.
right. So that we are considering the two-flavor Schwinger model with non-zero mass at theta equals 0. That is a gap. Yeah, gap space. Okay, so that state is represented by this. And next, I explain how to obtain the ground state or some excited state. So to obtain the state, we use the so-called density matrix renormalization group method, DMRG. This is a variational method to find the eigenstate of Hamiltonian. In this variation algorithm, we use a cost function, this energy. It is an expectation value of Hamiltonian. In this algorithm, the matrices A are optimized locally. And in this local approach optimization, we apply the singular value decomposition. And in this decomposition, only largest of the singular values are maintained. So the matrix size or bond dimension, D, is determined by this singular value decomposition. And so we use criterion to determine D by introducing the cutoff parameter epsilon. So D is determined by the epsilon, so that the truncation error of SVD is suppressed by it becomes smaller than epsilon. Like this. And epsilon is typically we choose very small number. So once we set the epsilon, the D is automatically determined by this constraint in the Schwinger decomposition. And as Kano-san said, and for gap system, so if we define the maximum one of this bond dimension, the effective, so the effective is independent of n. So the bond dimension is finite. So this is very nice property of MPS. And thanks to this, for gapped system, the numerical cost is just linear of n. So originally, the original state in Hilbert space is has the exponentially large degree of freedom, but now it's just reduced to linear. And this property, so the independence of n comes from the property of the entanglement entropy. Discussion of entanglement entropy in MPS. So in MPS, the entanglement entropy is roughly given by log of this bond dimension D. So the one dimensional system with one dimensional gapped system has a finite entanglement entropy. So the finite D is enough. Okay. So this is just roughly explanation of DMRG for ground state. So let me explain how to obtain the excited state. So the excited state, I denote psi k. K is a level of the level, index of level. Yeah. So the excited state is the lowest energy eigenstate under the orthogonality condition. This. So K prime is a level for lower state than K. So the psi K is orthogonal to any state lower than the K state. So using this fact, we can obtain excited state by DMRG by modifying the Hamiltonian like this. So here is the original Hamiltonian, and this part is a projection term. So this term runs from ground state to K minus 1 state. So this term plays a role of cost term, which implements, which impose this orthogonality like this. The cost function is there. And W is some positive weight parameter. And using this Hamiltonian, we can generate the excited state step by step. I mean, first we have to generate ground state because we use lower state here. And once we obtain ground state, we can generate the first excited state. Then we can go to second, third, and so on.
Isn't excited state degenerate?
Yeah, it's possible. But in that case, this method works nicely. Because this fact is also true for degenerated case, right?
I see. So you want to know just the energies, value of energy.
Yeah.
So,
and of course, but
yeah.
The given states can be mixed. I mean,
yeah. I imagine you get some superposition of excited states.
Yes.
When it's degenerate.
Yes.
Yeah.
If the degeneracy is a given state is some random mixture.
Yeah.
Right. That's right. But anyway, this method works.
Okay. And then when you want to distinguish excited state,
yes.
Then do you impose some symmetry conditions?
I will discuss later.
Okay.
Yeah.
Can I ask?
Yes.
Why didn't you calculate the eigenvalue of Hamiltonian itself to explore excited states?
Because I mean about this term.
Yes.
So this term is just imposing the lowest energy point, this point. And this term corresponds to orthogonality. So both of them are necessary. Right.
I thought that the spectrum of this theory is correspond to the eigenvalue of Hamiltonian.
Yeah.
But is it correct?
Yes.
So if you want to focus on excited states, you just pick up the not lowest eigenvalue of Hamiltonian.
Okay, I am. So if we can completely diagonalize this Hamiltonian, that's okay.
Yes.
But in practice, it's impossible, right?
Oh,
So
I see.
The point of this method is we obtain the state step by step from the bottom.
Yes.
And that's a strategy. Yeah, of course we can obtain some random state which also orthogonal to ground state, but that is just random state, so we don't know what is that.
Is it constant to the exact diagonalization to this Hamiltonian?
Yeah, for example, MPS is just approximated state.
Yes,
so in that sense, it's just approximation of the complete diagonalization. Yeah.
Oh, I see.
And actually, you can try that in the small system where you can use exact diagonalization. We can also use DMRG and compare the result of exact diagonalization and this method. And actually, the result is agree. up to the degeneracy. Yeah. Okay. And actually, in the calculation, we use the eigenstar library. Yeah, it's very nice, convenient library. Okay, and so this part I explain how to generate the state, and I also explain how to measure the observable. So observable is represented by some operator. After spin Jordan-Wigner transformation, the operator is represented by spin operator, and the spin operator can be transformed to the so-called matrix product operator, MPO. So this is very similar to MPS, but the difference is that the two spin indices actually. And there's a known algorithm that the spin operator is mapped to MPO. Yeah, it's almost automatically. Yeah. And once we represent the operator by MPO, the expectation value is given by contracting the all indices like this. For example, psi or psi is given by this. This green one is the MPS, and this is MPO. And also, it's possible that we can sandwich two different operators like this. Or also, we can compute the off-diagonal element. I mean, psi 1 or psi 2 is also possible. Yeah. So yeah, I explained how to the calculation method. And next, I go to the results. Okay. So as I said, there's three methods. So first one is the correlation function scheme. So let me define phi operator like this. This is the same one I showed in the previous page. And of course, this operator can be mapped to the lattice version, I mean staggered fermion operator, and then mapped to spin operator by Jordan-Wigner transformation. Then we can construct matrix product operator, so we can measure this operator, this value. And so we measure this correlation function defined value like this. So we put this operator at the position x and y with distance r. And there's some setup of parameter. I choose massive case and theta equals 0. The lattice size is order more than 100. And also, importantly, the cutoff parameter is around 10 to the minus 16 to up to 10 to the minus 10. This is a result of correlation function.
Excuse me, why did you choose this mass parameter?
We can choose any one. Yeah, maybe m equals 0 is not good.
Of course. But did you search the mass parameter space?
No. In this work, we just set only one single. M equals 0.
Why did you choose this 0.1 value?
No, there's no reason to specific to 0.1. But it's small enough to justify the bosonization calculation, but not too small. Like, if m equals 0, the two-flavor model reduced to the best Mino-Vitten model.
Yes.
That is CFT.
Yes.
In that case, the DMRG doesn't work well.
Yes.
So this maybe the middle of them.
Excuse me. So
yes,
in this theory, originally gauge coupling is included.
And gauge coupling, in this setup, actually the parameter physics is determined by the combination of G and M. And in this work, I just set G equal 1. Okay. Without loss of generality.
Okay.
Yes, thank you.
Did you take the continuum limit?
No, only this is
okay.
fixed.
I see.
Result, Okay. So this is the result of correlation function. So log of correlation function. So typically, correlation function behaves like exponential, so it's like almost linear. In this against the distance. And this different symbol represents a different cutoff parameter. The blue one is the most rough approximation, and the red one is the most precise approach. But in this plot, maybe we cannot distinguish the difference. So based on the conventional method in Monte Carlo, the
excuse me. I see. How did you choose the bond dimension?
I will. Yeah. Okay. So we usually it's convenient to calculate effective mass. It is given by this is a log derivative of the correlation function with respect to the distance r. So in discrete case, it's like this, and we take 3-point average to suppress the staggered the oscillation of staggered premium. Yeah. Anyway. So that in that sense, so this effective mass represents the exponent of correlation function. So in usual Monte Carlo simulation, we regard the Plateau value of effective mass as a meson mass. So let me see result. So the horizontal axis is distance r. So this is plot is the effective mass. So we can see some plateau-like behavior in large distance region. So usually we regard this plateau value to the pion mass. But this estimation is actually less precise. It gives less precise result. And in fact, if we close up this part like this, you can see some difference. For epsilon to 10 to the minus 10 is the most rough approximation with bond dimension about 400. It looks almost flat, right? Yeah, flat. So maybe we possibly misunderstand it, or it's just purely exponential. It's the purely flat means purely exponential. Yeah, but that is not actually incorrect. Because if we see more precise result with bond dimension is 7 times larger than this case, that point. So you can see that some R dependence here. It's not completely flat here. So the more precise results show some non-trivial R dependence, and which actually visible only if that bond dimension is large enough. So this is a very important point. So let me explain why. What is this R dependence? So this R dependence can be understood from the considering the free theory. So let me think about free particle in 1+1 dimension with mass m. So the correlation function, special correlation function of the free particle is in 1+1 dimension is given by the modified Bessel function K0. Yeah, this argument MR. And a asymptotic form of modified Bessel function is given by this for MR in that case. And so this is like a Yukawa type correlator. So if we compute the effective mass, log derivative of this guy, we get 2R 1 over 2R 1 over R term plus constant. This is sort of mass. So if we can regard the meson as a free particle for sufficiently large distance, the effective mass should behave like the 1 over R term plus m asymptotically. Yeah. This is the point. So it's not just a constant, not just a plateau, but some R dependence appears here. So based on this fact, let me study the one flavor case because massless one flavor single model. For this model actually is exactly solvable, and we know the exact value of the mass of composite particle. So let me check what happened. Yes. So this is the effective mass of the composite particle in one flavor model. Yeah, and it shows the R dependence. For larger epsilon, I mean the rough approximation case, it's again, you can see plateau behavior. But for more precise case, it's some non-trivial R dependence appears. And actually, the discrepancy is much larger than two flavor case. And so to distinguish this, to identify this 1 over R behavior, we plot the same effective mass against 1 over R. So the horizontal axis is now 1 over R. And so the left-hand side is long distance points. So you can see if we increase, if we make the epsilon small, I mean make the bond dimension large, the linear behavior appear like a difficult to see that. This is a red point. It's almost linear around here. So this is consistent with this prediction. I mean, 1 over R plus. And this.
Excuse me,
yes.
why did you consider one flavor case?
So we know exact value.
Oh,
I
I
just-
see. But this mass gap is larger than your two flavor case, I suppose.
No, I just try to test this scenario
I
in
see.
known
I see.
case
I see.
before I go to two flavor. Yeah,
I see.
and what happened? Yeah, yeah, and yeah, this exact value of mass is represented by this horizontal line here. So, and from this scenario, the mass is given by the R to infinity extrapolation of this one. I mean, the extrapolation to this y-axis here. And actually, if we fit the data for the most precise case by linear this function, we can estimate the mass by this, by fitting. And actually, this value is close. And actually, if we regard the plateau value of the most less precise one, we get maybe around 0.63 what, yeah. So it's much far away from, exact value. So you can see that this prescription, I mean the fitting by 1 over R gives more precise, more close result to exact value. So we think that this strategy is also applicable to two flavor case, where the exact value is not known. Okay, so we fit the effective mass by this 1 over R function for most precise one. So this is a result for pion. So we did, actually for this is also the same plot as the similar plot as this one. So effective mass against 1 over R. So this fitting line represents this extrapolation. So we obtain the pion mass here. And similarly, we can the same analysis for sigma meson and also eta meson. And thanks to the because the tensor network method doesn't have system statistical error, so these results doesn't have statistical error as well. So only we have systematic error, and the result is given by this. Sorry.
How about the finite size effects?
Finite system size effect.
Yeah, right.
Yeah. Thank you. So maybe. So in this plot is a log of correlation function. So the lattice size is almost 40.
Okay.
So this plot is just from the left boundary to middle, the center of lattice. Sorry. So this is a distance, so not coordinate. So it's a 黒板書いても大丈夫。I don't find in the slide. So this is a one-dimensional lattice, and here is the center, and we put pion operator, meson operator like this symmetrically. So here is x and y, and so this distance corresponds to r. So the r can be 0 to L. So 0 means just a local, it's local 2-point function center, and L in the L case it just covers the whole lattice. But of course, in that case, it's affected by boundary effect. So that's why I brought only up to 20. 20 is the half, so it's a halfway of just this picture.
But 2-point function in a finite system doesn't behave like just like exponential, but
right. So if we go increase more distance, it's maybe depend on the operator, but it maybe I remember correctly, it go up. Like a cosine hyperbolic behavior. So it's affected by boundary.
But it's not so large, even for the half, if you use half of the system.
Right. Because it's gapped system. So the boundary effect is typically decay exponentially. So if the operator, the point of the operator insertion is far away from the boundary, it's okay.
But for the operator at y, operator at x and the boundary is almost the same distance. So both of them are same exponential damping. So it's the same order or something. But at least your computation, the boundary effect is not negative. Okay.
Yes, and for example, boundary effect is more severe for eta meson. And actually, this fact is related to the next section. But and in fact, we subtract the disconnected operator to subtract the boundary effect as much as possible. So Python case we don't need to subtract, but
Okay. Thank you very much.
Of course, So ideally, we have to take an infinite volume limit to obtain more to compare the result with quantum theory. But in this analysis, it's just we want to investigate the effect of epsilon. I mean bond dimension. More precise, more specifically. So anyway, so there is some difficulty in the the setting of bond dimension, but we can obtain this mass result of mass meson mass. And okay, so next we go to the 1-point function scheme.
Excuse me. So could you see the previous slide? So do you have any reason why the alpha for sigma is
thank you very much.
very deviates from
the estimation of free theory, alpha should be 0.5, but maybe so pi and eta is close to 0.5, but this one is more larger. Actually, we don't know exact reason why it's so large compared with the other, but so the previous analysis is just a free theory. So this result suggests that the sigma is not just regarded as free part. Maybe it's due to the interaction, so it's not just a propagation of one particle, but some mixture of two particles, or many particle states can mix. But so far we don't know the explicit answer. So the next I explain the 1-point function scheme. So this is our alternative method which does not rely on correlation function. So in this method, we use the boundary effect as a source of meson. So in terms of condensed matter physics, so the boundary effect can be regarded as impurity or defect or some insertion of external field. And in fact, the one-point function or meson operator decays exponentially like this as a distance of the from the boundary. So this is a lattice, and there's a boundary effect like this. This green curve shows the one-point function, and it decays exponentially like this. And also, the other side is also exponential decay. So it's totally maybe cosine hyperbolic like. And from this exponent, we can extract the meson mass.
How did you identify the what the kind of boundary operator for this case?
Yeah, thank you. So in fact, it's unknown. I mean, we don't know actually what is the meaning of boundary operator here, but it can be some mixture of various state of quantum number, maybe. Yeah, and actually its behavior is different depending on the meson operator. Let me show example. So first one is eta meson. It is actually most simple case. So in this case, the open boundary at theta equals 0 can be a source of ice singlet meson. And actually, the meson one-point function of eta is behavior exponential minus mx. So this is a plot. So horizontal axis is a distance from the boundary x, and vertical axis is a log of eta. So actually, you can see that it's linear. So it means that it's exponential behavior.
So in this case, your claim is you interpret this one point function of eta prime eta meson is equal to something 2-point function with eta and some unknown operator.
Yeah,
I see.
It's a mixture of isosinglet operator. Yeah. So yes, and by fitting this slope, we can reach the mass. This, and the important point of this method is I brought the various value of epsilon, but there is almost no epsilon dependence is observed in the fitting result. So in this sense, the systematic error from the truncation is sufficiently small.
Excuse me, why in right figure, why near 0 and near 20 feeding works not well?
I mean, why it's deviate from
Yeah.
This is actually I don't know why. Maybe there is some or
where is the point one point function inserted? What is the meaning of the x?
Yeah, it is active. So yeah, so can you see this?
Yes.
So this is the left boundary.
Yes.
And 1-point function is inserted at coordinate x.
Oh, I see.
The 0, 0, this point is the boundary.
I see.
This is the center of lattice.
I see. And you regard this 1-point function as a 2-point function of one eta meson on at x and another one at I see.
So why
distance? So you have an effect from other boundary.
Yeah.
That's why.
So actually, the full if we for lattice, it's like a cosine hyperbolic, and so if we extend the plot region, it's go up. But it's basically symmetric, so I just only focus on left side.
Matsumoto-san,
Yes.
why there is no 1 over R correction in this case?
So yeah, why? It's not just correlation function, but just
But
this
the
1-point
mechanism must be same. So you generate some state at boundary, and so it's like boundary middle correlation function. So of course, if we get zero momentum state, there is no 1 over R correction. But I cannot understand boundary state is zero momentum state. What? It's zero momentum state? By some reason.
Yeah, possibly. Yeah, but Yeah.
Okay.
It's not known. Yeah. Thank you for question. Yeah, that's interesting point. Yeah.
And momentum is not conserved here, right?
Yeah,
Yeah.
because of the boundary condition. Yeah.
Right. Yeah. Yeah. Thank you very much. Yeah. Yeah, and actually this fact, the epsilon independence comes from the MPS is very good at represent the exponential some well, I should say that MPS is not good as express logarithmic correction of correlation function, but it's good at represent exponential behavior. And also, yeah, this is eta method, and also we can compute for sigma method case. So basically it's similar, but there is a constant shift in the bulk. So we have to subtract this constant part. It's resetting the value at the center, at the center point. Then we just fit the result by exponential and obtain the mass. Yeah. Basically, it's the same before. And again, we don't see epsilon dependent. So far, this result comes from the theta 0. So next we go to pion, but it's very non-trivial. And for pion case, if we measure the 1-point function of pi, actually it's 0 everywhere at theta equals 0. So we cannot use that method, but there is a possible direction. We set theta equals 2 pi. It amounts to introducing the background electric field, because the theta term plays a role of background electric field. So setting 2 pi is induce background electric field with magnitude 1. And in this setup, the Dirac fermions which have charge, electric charge plus minus 1 are induced at both ends of lattice. And this Dirac fermions has the isospin 1/2. So it can be regarded as the excitation of isospin 1/2 like this. So this guy can be a source of isotriplet meson. I mean pi meson. So this is a trick. And in fact, this phenomena can be it's related to the so-called SPT phase in condensed matter physics. So the ground state at theta equal to pi has a fourfold degeneracy in infinite volume limit, and this corresponds to the Halden phase of odd integer spin chain, which has spin 1/2 degree of freedom at the both ends of lattice.
Excuse me.
Yes.
Why 1-point function pion is equal to 0?
At
Theta equals 0. Yes.
maybe it's related to the isospin symmetry of the theta 0 value.
Oh, I see. But is it is there any contradiction with your understanding as a 1-point function is equal to 2-point function with operator and something?
In other words, so the boundary at theta equals 0 cannot be a source of isotriplet.
I see.
So this unknown operator includes a singlet meson, but not triplet meson. Yeah. And actually, this kind of excitation can be a pion operator. Yeah. Regarded as a pion operator.
Can you understand why the boundary effect only affect the spin singlet operators
at theta equals 0?
At theta equals 0, yeah.
So Matsumoto, I'm confused. Theta equal 2 pi is equal to theta equal 0?
Yeah, thanks. Yeah.
Why
If the manifold is closed manifold, that's right. But now we have open boundary. So the boundary
artifact of the boundary. So it's not topological term in that sense.
Yeah, in that sense, yeah.
Mm.
Yes. Yeah, and if we write a very rough phase diagram, so theta equals 0 is trivially gap phase, but theta equals 2 pi is Halden phase. And these two phases divided by the phase transition at theta equals pi, there is a very exponentially small mass gap.
But theta equal 4 pi is equal to 0, or you
Yeah,
have
yeah, I think so,
different
yeah.
phase again?
Yeah, trivial gap, Halden phase, and trivial gap, and yeah, it's
Okay.
yeah, exactly.
Repeat.
Excuse me. So classical thinking, so changing theta by 2 pi is just like a insertion of boundary Wilson line.
Yeah.
Right?
Right.
So apparently it is not related to isosmy, but it's related by anomaly, chiral anomaly, maybe. So chiral anomaly connects F to
Yeah,
some-
yeah, right.
something related to
Yes.
chiral.
Maybe, yeah,
May-
I'm not sure, but
maybe
yeah,
some-
it's possible. Yeah. Yeah, thank you. Yeah. So by setting theta 2 pi, we can perform the similar analysis. So this plot again the 1-point function of pi versus distance from the boundary. So around here you can see the linear behavior. It corresponds to exponential, and so we get pi on mass. So and not that we turn on theta term, but actually theta equal to pi is the computational cost of that point is almost the same because it still is kept. Okay, and in summary, we get this mass from this scheme. Okay, so finally we go the third one, dispersion relation scheme. So this scheme is totally different from the previous one. So in the Hamiltonian formalism, it is straightforward to treat the excited state. So we can obtain the dispersion relation like this directly. So by using DMRG, we can generate the excited state. And in this work, we generate the level up to k equal 23. So that 23 excited set and 1 ground set generated. And of course, we can compute energy of each state, and also we can compute the total momentum. Okay. So this comes from this is a description into Dirac fermion, and maybe you know this form of the momentum, and of course we can rewrite in lattice form. But note that this momentum operator does not commute with Hamiltonian due to the absence of translational invariance. Actually, we impose the open boundary. Open boundary actually breaks translation, and also we integrate the Gauss law condition, which also affects this translational invariance. Yeah, that's nice. Yeah, if we choose periodic boundary condition, actually the Hilbert space becomes infinite. So we can the similar technique by integrating the Gauss law condition, but in the periodic case only one bosonic degree of freedom remains that result in infinite Hilbert space. We have to truncate that one. So and also the MPS is not so good that represents the state in the periodic system. Yeah, it's good at open boundary. So yeah, so yeah, for such a reason we choose open boundary. So this operator doesn't commute, but still useful as an approximation operator. So let me show the result of the energy and the momentum. So we define energy gap delta E by subtract the energy of the case excited state from the that ground state. And also momentum square, I mean, we define the delta k square by subtracting the k square expectation value from the ground state. So the left figure shows the energy energy gap for each state. This horizontal axis is the level of the state. So you can see some degeneracy here. And also, this is a momentum. In this momentum, you can also see some degeneracy. Yeah. So we think that this triplet, maybe pion, and there's also some singlet, maybe it does be, maybe it's easy to see in this plot. Yeah, some singlet can be sigma or eta meso. But only from this plot we cannot identify them. So we measure the quantum number of each state.
Why you have triplet for 19, 20, 21?
19.
Because momentum is very
Thank
small.
you. Yeah.
So you have
I will
vector
discuss
meson?
this later. Yeah, actually. Actually, the 1, 2, 3, 4, 5, 6, these guys are pion actually. But this 19, 20, 21 is not just the usual pion. Yeah, I will explain later. Thank you.
Vector meson or?
Yeah, actually, it may be scattering state of pion. 2 pions scattering state. It's not completely confirmed, but yeah, combining some results from previous work, yeah, maybe it's
2 pion is maybe vector, right? Equal to vector quantum number.
vector. But this state
Low meson, like low meson or no?
Is that but this state has the same quantum number as pion. So
Same quantum number of pion.
Yeah.
Then,
maybe okay. Yeah.
but 2 pi, it must be
But
parity even or maybe because of
plus
angular.
the isospin, the combination of isospin one state result in one singlet and one triplet and one, let's say, the spin 2 state, maybe 0 plus 1 plus 2, I guess. So maybe this state correspond to isospin 1 state, from the combination of 2 isospin 1 state, I think. I think it has the same quantum number as pi. Yeah, also possible that the singlet states appear around, somewhere. Yeah. That's okay.
You fix quantum number, I can see you just pick up all eigenstate from the below. That is, I thought, your method.
Yeah. So I
So,
generate up to 23rd excited state. Yes.
so that means there is no pion quantum number, not necessary to be pion quantum number.
No.
Or why you said it's pion quantum number?
Yeah.
Because you have triplet and singlet at the same time. So
Yes. Yeah, we can. Yeah, we have triplet and singlet. And this right figure shows the triplet state. I mean, yeah.
okay. So after calculating quantum number,
Yeah. Okay. So first of all, we can distinguish the triplet and singlet from how they are degenerate. From seeing just value of energy, and we can categorize them to triplet and singlet. Then we can measure the isospin operator defined like this. Actually, isospin completely commutes is Hamiltonian, so it can be good quantum number. And also we can define charge conjugation. On the lattice, it can be implemented the one-side translation, but anyway, yeah. But for charge conjugation, it's not completely commute with Hamiltonian due to the boundary effect. Yeah. But anyway, we can still, use the approximated operator. And also, but know that the charge conjugation can act on the only charge neutral state. So that for nice quantum number is a G parity. The so-called G parity is a charge conjugation and exponentiation with an isospin operator. Yeah. So anyway, we can measure such operator, and the pion should have the quantum number J equal 1. J equal 1 means that J square equal 2, and JZ equals 0 or plus minus 1. And also G parity should be positive. So let's see this table. So for example, 1, 2, 3, triplet has J square as almost 2. And JZ, this is actually after the result after diagonalization. So we can see clear plus 1, 0, minus 1. And G parity is positive number. The reason why it's not unity is due to the boundary effect. Yeah. So in that sense, we can identify this state as this pion state. And also, we can pick up singlet states here. And the J square is actually 0. It means that J has been 0 state. And Z also 0. And G parity is different. And for Z parity, positive state, except for ground state, is 13, 14, 22. So they are consistent with sigma meson. And also, G parity negative state, 18th and 23rd, can be regarded as eta meson. We identify the meson by this method. And as Alex pointed out, so 19, 20, 21 has the same quantum number as pion, but the momentum is much lower than the other pion state. And so, okay, for each pion state, we plot each meson state, we plot the energy against the k square, momentum square. So we obtain this plot. So this blue square corresponds to pion state. I mean, these states. And orange one corresponds to sigma meson. And eta is represented by this green one. And the 19, 20, 21 state is here. So it's far away from this pion dispersion relation. Yeah. And the energy of this state is almost much more than 2 times larger than pion, the pion lowest mode. Yeah. So in that sense, maybe it seems to be 2 pion scattering state. And a similar state is found, it was found in this paper in 1994. Yeah. Okay, so and by fitting this data point by this formula, we obtain M here. So it can be regarded as pion mass, sigma mass, and eta. Yeah. So let me summarize. So we propose 3 results, 3 methods, and the 3 results obtained by this method are consistent with each other, plotted this. Of course, there's some small deviation, maybe which comes from the finite spacing effect. And finite spacing effect can depend on the method in general. So maybe if we take the quantum limit, this point approach, yeah, I guess. And also, yeah, this result is consistent with the analytic prediction. For example, this ordering of mass by sigma eta reproduced. And also, the mass of eta is around 0.9 is consistent with estimation. I mean, mu plus order M correction. In this setup, mu is 0.8 and M is 0.1. And also, there's a prediction about the ratio between sigma meson mass and pion meson mass, which should be square root 3. And this is a value of the ratio. The square root 3 is 1.72 or something. So these results agree with this one within the 5%, 5% deviation. And note that this is just a result from Sine-Gordon approximation by Sine-Gordon model. So it's not necessarily completely agree. Yeah, so it just approximation. Yeah, but so this maybe this results suggest that the Sine-Gordon model is very nice to describe these pions. This method. Yeah, and let me discuss the feature of each method. So the first one, the correlation function scheme. So the advantage of this method is applicability, wide applicability to any other models in maybe higher dimension or more larger lattice or any case. And also correlation function accept off diagonal components. Yeah, I will explain the next slide. And but the disadvantage of this method is that this method is sensitive to the bond dimension of MPS. I mean, we have to increase the bond dimension. Yeah, but this point can be maybe I expect this disadvantage can be solved by quantum computer, because in the quantum computer there is no we don't need to restrict bond dimension. Can be infinity. So and okay, next one-point function scheme. So in this scheme, we need to increase neither of the bond dimension nor the system size. So in that sense, it's a very economical method. It's very low computational cost. But this method strongly rely on the property of the model. I mean, we need some prior knowledge about the model. So in that sense, maybe we cannot apply this method in any time. And the third one, dispersion relation scheme. So we can obtain various states heuristically. I mean, so in the above method, we first specify the operator which corresponds to some meson and measure it. But in the third method, we don't need to know anything about the operator. We just generate eigenstate and look into them. What is that? Yeah, so it's a very different strategy. And also, so we have each state itself, so we can directly see some wave function or some property of each state. But the difficulty is that in fact, it's difficult to increase the system size, because so the momentum is discretized by 2 pi integer over L. So if we increase L, the step size of discretization becomes smaller and smaller, and there are many momentum excitation accumulate before we reach the other sigma meson. So maybe in that case, we have to generate more and more states. And also, the problem is the computational cost. So compared with the other method, we have to generate many excited states. So it's require more additional computational cost simply. And also, I'm not sure how to efficiently generate excited states in quantum computer. That's the question. So let me explain future prospects. In particular, maybe we are interested in non-zero theta region. So what is the difficulty in the non-zero theta region compared to theta 0? So one is that meson operator are mixed non-trivially. I mean, so the theta term mix low log operator of, for example, eta and sigma. So it's a rotate in the complex plane of scalar versus pseudo-scalar observable. So shortly, so you have to compute this kind of correlation matrix. So S means scalar operator and PS means pseudo-scalar operator. So we have to compute this kind of correlation matrix and diagonalize it. Then the eigenvalue becomes the correlation function of some meson, corresponding meson. So in that sense, the correlation function is okay, but the one-point function is I'm not sure how to taking into account this kind of mixture. And also, non-zero theta, the theta term explicitly break charge conjugation and parity. So they cannot be a good quantum number in that case. And so also, in the tensor network, the approaching theta equal pi means approaching gapless phase, so that we have to increase the bond dimension. It's also problematic. But maybe we can, but still we can use MPS. Maybe it's not good at just on theta pi, but we can approach pi. And also, the other kind of tensor network, such as Mera, maybe can possibly useful, or also quantum computation is also possible direction. Thank you for listening.
Thank you for very interesting talk. Is there any questions or comments?
So,
please.
Honda-san, please go ahead.
Okay, thank you. Yeah. So, is there any comparison to continuum result beyond the square root 3?
So far, we only have, just these comparison. For example, if we measure the mass by changing fermion mass, we can see mass dependence. Like this, and also theta dependence is also. So, if we can perform such an analysis, we can compare, them. But now we just fix M and theta, so it's up to that 3 comparison.
Okay, thanks.
Aoki-san, please.
So in the summary slide, you said the order error are different, but I don't think spectral quantity has different order errors. So maybe your method has error, but definition of mass should not have mass shouldn't have different order error because its spectral quantity determined from Hamiltonian. Of course, your extraction may have some systematics.
That's I understand.
And also, I like third method. It's most
it's very
Hamiltonian like calculation.
Yes, maybe this discrepancy comes from some systematic error from
how to extract the value.
That's right. I think
if you know 1 over r behavior, you can just fit 1 over r exponential. Something.
Right.
Instead of effective mass.
Thank you.
Can I ask?
Yes.
Did you compare your result to the Monte Carlo one? Your calculation seems to the theta equal to 0 results. So
I think some notation different and also parameter setting different. So far we didn't compare to the other. But one possible comparison is this one. So this is the work in 1994 using the so-called lifelong term Dunkel approximation. I'm not familiar with this method, but comes from some knowledge in some nuclear physics or something. And in this method, actually it's a Hamiltonian formalism. And sorry, it's because they calculate the mass spectrum depending on the fermion mass. So the horizontal axis is fermion mass. Maybe some normalization can be slightly different, but basically I think similar. And here 0.1 corresponds to our point, and this curve corresponds to pion. So this represents pion mass, and it's I think 0.6, but I think this mass normalized by some maybe mu, I guess. If I remember correctly, yeah, this horizontal vertical axis is normalized by mu. So considering that point, if I remember correctly, this value is almost same as our result. Yeah, and they also find sigma. So they don't call sigma, but they call pi bound state. Yeah, it's this one. And also eta. Yeah. And also the pi scattering state appears here. So this state corresponds to, I think, 19, 20, and 21 excited state in our analysis. So in that sense, we can compare. Yeah.
Is it result from the Monte Carlo simulation?
No. This is
some kind of
yeah,
approximation.
it's Hamiltonian formalism, and if my understanding is correct, so first they consider the light cone quantization.
Yes.
And in the Fock space, they consider Fock space and restricts the maximum number of the Fock set in the Fock space, and then truncates the Hilbert space. And they obtain some approximated Hamiltonian, and they exactly diagonalize that. Then they obtain.
Is there any other questions?
Pion sigma meson bound state.
So they call sigma meson. They regard sigma meson as the pi bound state.
So then it's like a pion, 3 pion state or something.
I don't know, but this guy is a pion scattering.
Pion state. But quantum number is like a pion sigma meson bound state. Your state is like a pi, same quantum number as a pion.
Okay, there are some not one, but there are some pion pi scattering state. So
okay,
I think pion combination of two pion can be singlet as well as triplet. And the triplet part appear here, and the singlet part yeah, somewhere the pi scattering in singlet. So yeah, scattering state split into triplet and singlet. Yeah.
So your state is your state has the same quantum number as a pion.
I think so. Yeah. In this the pi scattering in triplet is same as pion, and pi scattering in singlet, I'm not sure about it. Yeah, can be different. Yeah, maybe I'm sure.
Okay. Thank you very much.
Is there any other questions? If not, let's thank Matsumoto-san again.
Thank you very much.